Hello everyone, my name's Josh Brooks. I've been responsible for some of our hardware research and selection, primarily that of sensor peripherals. And we are Octodata. We're a team working again with the Humanoid Biorobotics and Smart Systems Research Lab here on campus. Our project is in the field of soft robotics. It's centered around an existing robot prototype that's meant to mimic the appearance and movements of an octopus. The robot has 4 tentacles made of silicone that can coil and grasp objects underwater. In addition, it's able to maneuver vertically underwater by means of a pneumatic buoyancy control system. Currently, the robot is able to do these 2 things based solely on wireless input that's processed by a microcontroller. And our project goal is to improve this solution by using the more powerful NVIDIA Jetson TX2 developer kit, which will support computer vision and autonomy features, all while including more onboard sensors and keeping the control circuitry as simple and robust as possible. So with that introduction, I'll let my colleague Brian introduce and give an overview of our proposed solution.
Hi, my name is Brian Tilley. I'm responsible for computer vision, algorithms, and software engineering, so that basically covers the camera system of the robot. We see the octopus-like robot being used in the oil and gas industry for automated inspection, maintenance, and repair, which is summed up in our demonstration that we plan to perform at the end of Senior Design 2, where we'll have the robot recognize the lever, use the pneumatic buoyancy control system to reach the lever, and then grasp and manipulate it. To make the analog between the oil and gas industry, the robot will also need to find specific locations, travel to them, and then actuate mechanical controls. So that's the reason for the demonstration. To accomplish this, we'll be developing multiple control systems, which are electronic muscle actuation and power circuits, the limb tension motor control circuit, and the pneumatic buoyancy control system. We'll be fleshing those out and progressing them forward. We're also adding 4 elements of sensing, which are, of course, computer vision via the NVIDIA Jetson TX2 and an attached camera, external water pressure, internal environment sensing, and an inertial measurement unit, which tells us how the robot's moving over time. The robot, as Josh said, will be able to operate either autonomously or, as it has in the past, with manual wireless control input. In order to make the robot more compact, robust, and easy to build, we'll be designing printed circuit boards, which replace the previous team's temporary construction. Because we're operating with electronics underwater, safety has been and will continue to be a driving factor in our design choices, which is covered by elements like choosing safe components such as the battery, implementing safe hardware and software failure states, and then including easily accessible emergency power disconnects. So thank you for listening. We'd like to take any questions.
Are you planning to use a umbilical cable from surface to whatever the device is deployed?
No, sir. It's going to be fully self-contained with a battery on board.
What kind of communication are you planning to use? What type of communication?
So wireless communication, we're considering 2.4 gigahertz and then the XP protocol.
Through the water?
Yes, sir.
How deep?
It's
less than 3 meters.
3 meters, yeah.
Oh, okay.
The end goal would probably be to, of course, make it fully autonomous. So at the end, the intention would be wireless communication would be a safety protocol rather than actual control.
Okay.
So if you're only going down 3 meters, what kind of application in oil and gas are you planning to target with that?
That would probably be far future. This has been a long, several-year process for the HBS lab, so it would be iterating. We're providing, for instance, the IMU. We're providing extra sensors that future teams can use to improve.
The difference between this being a soft-type robot as opposed to what they're doing now with just clamps and things of that nature, why do this instead of the previous processes?
So if there are any situations where we have delicate controls or devices that can't handle being grasped with more rough actuators, soft limbs would really shine, and then they can also somewhat conform to the surface of whatever you're trying to grasp, instead of just hard contact.
Okay, and this demand or use was, how was it determined? Is it by the oil and gas industry saying that they need that, or what's kind of started this idea?
It seemed like a good way to demonstrate the usefulness. There's no clear demand, but I mean, I could see it being useful.
So if I may,
Go ahead.
the soft limbs are one of the key technologies of the HBS lab, and they were included in the Octopus-like robot beforehand, and we just want to show them off and also develop the control behind it.
So the Octopus is not their idea. It's already a project
Oh,
existing
okay.
on campus, and
Right.
they are enhancing the project.
Like I said, we're
Okay.
taking a project that's been in development and we're iterating on it.
Right, and we're modifying it from being a purely manual thing to being a manual, it's still manual, but also has these autonomous features that we can kind of turn on and off.
Okay, let's thank the team.